The Tundish is a critical vessel in continuous casting, acting as a buffer between ladle and mold. Beyond flow distribution, it serves an important metallurgical role, enabling non-metallic inclusion flotation for cleaner steel. Flow control devices, such as pouring boxes, are used to optimize flow patterns, minimize short-circuiting, and promote effective inclusion removal. We begin by observing the flow in a bare Tundish, without any flow modifiers. Dye is injected at the ladle shroud to simulate the entry of molten steel laden with inclusions. The jet impinges on the Tundish bottom, travels along the floor, and exits through the outlets. This results in short-circuiting of flow, where inclusions have limited residence time to float and are more likely to escape with the outgoing steel, compromising steel cleanliness. Now, we examine the Tundish equipped with a cuboidal pouring box. As dye is introduced, the incoming jet from the ladle shroud strikes the bottom of the pouring box, travels along the floor and is then redirected upwards by the side walls of the pouring box, promoting surface-directed circulation. This redirection increases residence time by eliminating the flow short-circuiting observed in the bare Tundish, and promotes the flotation of non-metallic inclusions to the slag layer, thereby enhancing steel cleanliness. The previous demonstrations assumed single-phase flow, where only liquid steel, represented here by water, flows through the ladle shroud into the Tundish. However, in actual industrial operations, gas aspiration into the ladle shroud is a common occurrence during ladle to Tundish transfer. This happens due to imperfect sealing between the ladle shroud and collector nozzle, as well as microscopic structural irregularities at the joint, allowing entrainment of ambient air and shielding gas, typically argon. To illustrate the effect of gas aspiration on Tundish flow, we now inject dye under controlled gas loading conditions, with a gas-to-liquid flow ratio of 10%. In the absence of gas aspiration, the liquid jet enters the Tundish, impinges on the bottom of the pouring box, and is redirected upward, enhancing residence time and promoting inclusion flotation, as discussed earlier. However, in the presence of gas aspiration, the resulting buoyant gas-liquid mixture causes premature jet reversal, even before the flow reaches the bottom of the pouring box. This early reversal occurs due to the enhanced buoyancy introduced by the entrained gas phase, which inhibits deep jet penetration. Consequently, the interaction of incoming jet with the pouring box is disrupted under these conditions. Additionally, turbulence levels increase in the entry region of the Tundish. Such changes in the flow field may significantly alter inclusion flotation behavior and mixing characteristics. While early jet reversal might reduce short-circuiting, the increased turbulence and irregular flow paths could hinder inclusion removal or even promote re-entrainment. Therefore, the overall effect of gas aspiration on steel cleanliness is complex, and its net impact must be evaluated carefully through further physical modeling, CFD simulations, or plant-scale trials. In summary, we have visualized the critical role of Tundish flow patterns in governing steel cleanliness during continuous casting. In the bare Tundish, short-circuiting of flow limits residence time and hinders inclusion removal. The use of a pouring box effectively restructures the flow, enhancing upward circulation and promoting inclusion flotation to the slag layer, a key step toward cleaner steel. However, the third case highlights a common industrial reality. Gas aspiration into the ladle shroud introduces a buoyant two-phase jet, which alters the designed flow path by causing premature jet reversal and increasing turbulence near the entry zone. While this can affect Tundish performance in complex ways, the net impact on steel cleanliness requires careful quantitative evaluation through additional experiments and simulations. Ultimately, these physical model insights underscore the importance of flow control devices and operational conditions in designing and maintaining effective Tundish systems for high-quality steel production.